So, in this lecture we will take the review of continuum mechanics that we have been doing in last couple of lectures to somewhat of a logical conclusion, where we are looking at the behavior of rubber. So, what we essentially stated in the last lecture, and we took it for granted in the derivation, is the free energy of deformation of the rubber is a function of the deformation gradient tensor. So, we will first establish that by using what is known as the Coons theory of rubber elasticity, and then using these ideas we will look at various kinds of deformation of a material, and we define what is known as the shear modulus of a polymer network. So, we will talk about the Kuhn's theory of rubber elasticity. So, rubber, as you know, is a polymer network, and therefore we can represent the rubber as composed of many polymer chains connected together by some kind of a physical or a chemical cross linking. Typically, when it is chemical or covalent cross linking, then that's what we call it a rubber. When it is a physical cross linking, we call it an entangled polymeric system. There is some difference. We also are doing it for the case when there is no solvent. When we have a polymer network in a solvent, we call it a polymer gel. That is somewhat more complicated in terms of formulation than what we are doing here. So, if we take this kind of a network, then these junctions are what are known as cross links, and between every two of these cross links we will have a polymer strand, so as to speak. And as you can see in the way we have drawn, the polymer strands in the entire network can vary in their end-to-end distance and their number of repeat units, because if you think of like how this kind of a thing would be synthesized, you will put polymer solutions in a beaker, then you add a cross linker, and the cross linker will cross link the polymer chains in a somewhat of a random fashion. It is very difficult to get a perfect network that would have a fixed number of repeat units between two cross links, and of course they will vary with regard to the end-to-end distance, because the system can take many conformations now, because every individual segment or a strand can take many conformations. These strands can also be referred as subchains, because they are not really an entire polymer chain that we started with. It is the polymer chain between the two cross links that is somewhat constrained now, because it has to move along with the cross links that connect them together. Okay. So, because of this cross links, the motion of polymer segments become somewhat constrained, and that is what give rise to a solid nature to rubber. If it is not cross linked, you will have like a polymer solution that can be viscous, but not quite like an elastic solid. Once you cross link it, it starts behaving like a solid. All right. So, these guys that vary in the end-to-end distance and the number of repeat units is what I refer to as a strand. And there are many strands present in the system. So, let us say we have a certain volume of the network. Let us say we have a certain volume of network. We can define a number of strands per unit volume, that is my NC, and we will use that later. Okay. So, if I now look at the free energy of this particular network, one point to start with is we can assume that each of these strands is an ideal chain itself. Okay, that may not necessarily be the case, but this is at least a good starting point to start thinking about it. So, we can define a reference configuration that is completely theoretical in nature, that is just reference. So, we can talk of free energy with respect to or relative to that reference configuration, and that reference configuration contains all ideal chains as strands, or all strands as ideal chains. So, we are going to assume reference as all strands are ideal chain. And the advantage of doing that is obvious. We already know what the elastic energy of an ideal chain is. So, for a strand of end-to-end distance vector RE and n repeating units or segments, we can write the free energy as equal to the elastic energy, which is given by this that we have derived for the ideal chain. Now, of course, that strand will not really have a fixed number of repeat units. The number of repeat units can change for different strands. Similarly, it will not have a fixed RE. The RE value for every strand can be different. In fact, for the same strand at different time can be different. So, in reality, what we do have is a probability density for a strand to have end-to-end distance vector RE and n repeating units, and we have to multiply the free energy with this probability density and integrate over all possible values of n and all possible values of r, and then only we can get the total free energy or the average free energy of an strand. And if I then multiply that with the number of strands per unit volume, we can get the free energy density. So, this is what we will do. So, I can write the free energy of network as the number of strands per unit volume integral of dRE, that is the integral of over all possible values of RE, integral over n n can take values theoretically from 0 to infinity multiplied by the probability density PREN and multiplied by the energy that we have for a strand of n repeat units having an end-to-end distance vector RE. So, if I look at this term here, this is some sort of a joint probability density, that is, first the probability of the chain having an end-to-end distance RE, and second the probability that the chain will have n repeat units. These two probabilities must be multiplied to get the joint probability PREN. So, this I can write as P of RE and P of N. This we have already derived for the ideal chain. It is a Gaussian function. And this we have not quite derived, but it should satisfy the normalization because ultimately the probabilities must normalize to 1. So, we know at least that thing about this function. So, now if I look at the deformation of this material, we can talk about deformation from this reference state, and again I want to emphasize here the reference state is hypothetical in nature, because we have to define some reference to compute the free energy difference. So, we have defined the strands being ideal as the reference state, and then we are talking about of changes from that reference state. So, if we think of a deformation in the material, the deformation will result in changes in the RE of individual strands. In fact, the REs will become some RE prime, and I can write this RE prime in terms of the language of deformation tensors that we have discussed, because just to recall, the deformation tensor is the derivative of the current position with respect to a reference position or initial position. So, we can do the same thing here. In this case, we will have something like RE prime alpha and RE beta, where RE refers to the reference state, and this becomes E dot RE. Okay. So, now if I talk of the free energy change, just to keep in mind that the free energy we have defined here is already normalized. So, it is free energy per unit volume, because we have defined the number of strands per unit volume. So, if I now talk of the free energy in the final state, where the strands have an end-to-end distance RE prime as opposed to RE, assuming that the elastic free energy expression that we have derived for the ideal chain still applies, that in fact is only true for small deformations, we can get the final energy as multiplied by RE prime square, which essentially is E dot RE. squared, and from there I can take now the free energy difference between the final state and the reference state, and using that I can get the free energy of deformation. And this is what we have used in the discussion of last class. Which is essentially F minus F naught, and which is equal to and this you can notice that is a function of the deformation gradient tensor, and that is the reason why we called it f of E. Okay. So, now we have a clear motivation that why for polymer networks we can write the free energy of deformation as a function of the deformation gradient tensor. And again, to recall, this is similar to f of phi, because just like we can think of the initial position with respect to previous position or the reference position, we can also think of the final volume fraction relative to the initial volume fraction, and that would be what we had for the Helmholtz free energy density we used while talking about thermodynamics of polymer solutions. Similar idea is at work here. Again, we are doing thermodynamics. The only thing is we are looking at a polymer network where only the elastic energy is important. If we are doing for the gel, we also have to include the chi terms, the effect of solvent, into the model, and then we can look at what is known as the swelling behavior and collapse behavior of polymer gels, but I am not going into details of that now. So, I will not completely derive this equation, but keep in mind that we have the probability density function that we have defined to be a Gaussian function multiplied by Pn, that is being normalized in this particular way, and on solving what we do get is the following. So, when we have done the work done in the previous lecture, we have just assumed that f is a function of E. We did not take the functional form into consideration because we did not know it back then, but now we have a functional form. So, now I can go back to the work done as a function of free energy relations and then try to look in more detail the stress tensor and so on for this polymer network. So, going back to what we derived, in last lecture, we had the stress tensor is equal to E beta mu dou Fe by dou alpha mu minus P of delta alpha beta. So, now since we have derived Fe as half Nc kBt E alpha beta square minus 3, I can equivalently write this as because anyway beta is repeated in the relation, it is a dummy index. So, I can change with mu just as we have been doing in other examples. So, now we can get the derivative as NC kBT E alpha mu, and therefore, we have so we will identify this quantity as my shear modulus G for the regions that will be clear in some time, and then this will be equal to this. Okay. So, now let us assume a shear deformation because we have identified this G as a shear modulus. So, let us assume a shear deformation and see what the expressions become that would explain the idea that why we have identified NC-KBT as the shear modulus. So, if I have a shear deformation in Cartesian coordinates, r becoming r prime is equivalent to x, y, z becoming x prime, y prime, z prime, and the way to visualize a shear is we assume some initial state as a rectangle in xy. We also have a z direction, but we assume that shear is being applied in the xy. So, this is my x, this is my y, and then perpendicular to this will be z that I am not drawing here, and this is my initial state. It is also unit in z direction, unit in x, unit in y, and we apply a shear deformation along the xy plane, and then this material deforms to something like this. This is the final state and this was the initial state, and this magnitude is what we know as the amount of shear. So, it is per unit the distance in the y direction, we have a shear y on the along the x direction. This is how we define the shear. So, then the positions actually transform as this. So, let us say we have a point right here, this point in the final state comes there. So, this point moves along x by gamma and it does not move in the y and z direction. So is true for every other point we can draw in the system. So, let us say we had a point here, this point retains the same y and z coordinates, only changes along the x, and we can actually do it for any point in the material, even that is not on the edge, they will also essentially retain the same x and z, same y and z coordinate, only change in the x coordinate. So, given this particular deformation, this is also called simple shear, we can define the deformation gradient tensor as dou x prime by dou x, dou x prime by dou y, dou x prime by dou z, dou y prime by dou x, dou y prime by dou y, dou y prime by dou z, dou z prime by dou x, dou z prime by dou y, dou z prime by dou z, and this using the relations we have here, dou x prime by dou x actually is simply 1, dou x prime by dou y is gamma, dou x prime by dou z is 0. Similarly, in the second row we have 0, 1, 0, 0, 0, 1. So, if I now look at the sigma alpha beta that we have found to be given by this relation, we know the shear is being applied in the xy direction. So, there is, that is perpendicular to the xy plane. So, perpendicular to the y y axis. So, essentially we are looking at sigma xy, that is the only non-zero component in the stress tensor. If I, for example, look at sigma xx, sigma xz and so on, all these has to be 0 because stress is only applied perpendicular to the y axis along the x direction, that is the direction we have. This is this particular direction. So, if I look at that term, that is going to be z of E x, and mu is a dummy variable. So, it has to be summed over all possible values of mu, that is x, y and z. So, E x x beta is y, E y x plus E x y, E y y plus E x z, E y z, and of course Kronecker delta of x y is 0. So, we do not have the last term. So, this is equal to E of x x is 1, E of y x is 0, E of x y is gamma, E of y y is 1, E of x z is 0, E of y z is also 0. So, this is g multiplied by gamma. That tells me that the stress that is being applied, it's only stress, we can call it sigma, is g multiplied by gamma, and this is how we define the modulus. The stress by strain is a modulus. So, in this case we apply a shear. So, stress by the applied shear is my modulus, and that is will be a shear modulus, and that is the reason why we had identified NCKBT in that equation as my shear modulus. So, we can also go ahead, try to look at other components of the stress tensor in this case, knowing that it is anyway 0, because we know that the stress is only applied in the xy, stress components in all the other directions are 0. Okay, but knowing that, we can try to compute it. The advantage of doing this is we can get the value of P from there. So, let us say if I am doing sigma xx, that is going to be g of E xx e xx plus e xy e xy plus e xz e xz, and now the last term will remain because we have delta of xx there. So, this will be equal to g exx is 1 dotted with 1, exy is gamma dotted with gamma, exz is 1 is 0 dotted with 0 minus p. So, this gives me g of 1 plus gamma square minus p, which has to be 0 because there is no other stress. This tells me that p must be g multiplied by 1 plus gamma square. Okay. So, this is how we can analyze the shear deformation. So, we can apply similar kinds of ideas to other kinds of deformation like uniaxial deformation, and we will continue the discussion in the next lecture. So, with that I conclude here. Thank you.